Hello, everyone. Welcome to the second talk in the second webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We hope that all our attendees and their families and their colleagues are safe amid the ongoing COVID-19 pandemic. We thank everyone for attending the webinar today. The webinar series in the spring of 2020 was an immense success, and the recordings of those webinars continue to be viewed on YouTube. Based on that success, the IAS has decided holding webinars, though in a slightly different format and sequence. Over the next year, we aim to host one webinar per month. Speakers will include international experts from both industry and academia, as well as PhD students and early career researchers. Subsequently, webinars will be announced on the IAS mailing list and the IAS Twitter feed. Today's webinar will be presented by Professor Handan Tezel of the University of Ottawa here in Canada. My name is Arvind Rajendran. I'm a professor of chemical engineering at the University of Alberta and a part of the IAS. I also have David Donacci from Imperial College who will moderate the sessions today. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you're not already. Our dues are minimal, only $20 US per year, but they do support the publication of our flagship journal, Adsorption. They contribute to travel grants and workshop seed funds for IAS members and affiliated groups, as well as aid organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS supported materials, including our journal, as well as the adsorption database provided by Springer Materials. Anyone can follow IAS on Twitter at @IntAdSauce for future updates regarding IAS events, webinars, and information about scientific meetings. Please do expand our YouTube channel by subscribing. At this point, I will hand over the proceedings to David Donacci from London.
Thank you very much, Arvind, and welcome everyone. It is my pleasure to introduce Professor Tezel, who is currently a professor at the University of Ottawa, where her research interests span gas separations using both adsorption and membranes, and also works on energy storage and biofuels. She completed her PhD at the University of New Brunswick, where she also stayed on as a postdoc with Doug Ruthven for a short time, and then joined the University of Ottawa as an assistant professor in 1988. Since then, she has taken sabbatical leave at Air Products and Chemicals, and has also been a part-time professor at École de Mines de Nantes and Tianjin University. Professor Tezel is also involved with a large range of professional bodies and organizations. She is a member of the Energy Task Force for the Ontario Society of Professional Engineers, and is the vice chair of the adsorption and ion exchange area of the AICHE. She is also an executive board member of the International Adsorption Society. During the webinar, questions can be submitted via Zoom or the YouTube chat. I will be moderating both of those, and we will have two question sessions, once at some point during the middle of the talk, and then once again at the end. So please submit your questions there. With that, it is my pleasure to welcome Handan, and please take it away.
Thank you, David. I'm going to share your screen now. And yes, can you hear my screen? Can you see my screen now?
Yes, everything seems to be working fine.
Great, great. Thank you very much. Good morning, everyone. Good morning, good afternoon, good evening, wherever you are in the world. Thank you for the introduction, and I would like to thank the International Adsorption Society for this opportunity. So Today I will be talking about determining binary adsorption isotherms using concentration pulse chromatography. So by definition, if we're talking about separations, we have at least two components, and we really need to determine how these two components or mixture components behave in the presence of other components as well. And this is a very important task to be taken up before we design any separation system. So in this talk today, I'm going to focus on binary systems that we have worked on, but as time goes on, I will show some examples of other systems, and I'm going to show comparisons with other methods as well. So here's a typical pure component adsorption isotherm. So it's basically on the y-axis, we have the amount adsorbed as a function of pressure. So the blue curve actually indicates the isotherm. This is for a pure component isotherm. And then as we know, as pressure goes to approaches zero, when we take the slope of that isotherm, that gives us the Henry's law constant, which explains the behavior of this component at very low concentration. So basically, this is the slope of the isotherm, and that's what we can actually get when we use chromatographic systems. And then we use this determining the slope, and we can extrapolate to determining the pure component isotherms as well as the binary isotherms. So as you can see, hopefully you can see my arrow there. So if we look at the slope of this isotherm, as you can see, as pressure increases, the slope will increase because this is a typical isotherm, Langmuirian, a favorable type isotherm, where as I increase the pressure, slope will decrease. So how can we use that to actually determine pure component and binary isotherms? So what we do is we have a setup. We would have to have a setup like a gas chromatographic system. Here is on the left upper hand side here. We have a gas chromatograph oven that is controlled at a certain temperature. And so what we have here is this is our adsorption column packed in the gas chromatographic oven. Remember that we're not using the gas chromatograph to determine compositions. We're using the gas chromatograph to get some peaks, and I'm going to talk about what kind of peaks they are and how we can use them to determine pure and binary component isotherms. So in a typical gas chromatograph, you would have a carrier gas. In this case, we have the option of a mixture carrier gas, but we can use it for a pure helium as well. So as you can see here, this is a diagram that I have taken one of our papers with Dean Kennedy, but it could be the carrier gas, could be your helium gas, it could be nitrogen, carbon dioxide, whatever you have, depending on what you want to do. And I will talk about different examples, example experiments that we can do, and how we use isotherm. So that is the carrier gas. And then by using mass flow controllers, we can control the composition of the carrier gas. So this goes through the thermal conductivity detector here within the gas chromatograph on the reference side first, so that we can create a voltage. So after the reference side of the thermal conductivity detector, it goes through the injection valve where actually the sample gas is injected. So this is, as you can see, we have the nitrogen and carbon dioxide as an example here, but I want to emphasize that we do not inject mixture. We inject only one component at a time. So either, let's say, nitrogen or carbon dioxide or any other sample gas that you will have to be connected here. So basically the carrier gas takes the injected sample and goes through the gas chromatograph. It goes through the coil first so that it goes up to the temperature of the column, and then passes through the column, packed with the adsorbent that you want to work with, and then goes through, and then we monitor the outlet composition, where the carrier gas goes with the sample, goes through the sample side of the thermal conductivity detector. And since on the reference side, we have the pure carrier gas or mixed carrier gas, when we inject a sample here on the sample side, there will be a voltage created, and then we actually monitor this voltage change, and then it's ventilated. So that's how the chromatographic system works. So here is a typical example of the response of the system, of the system as a function of time. So keep in mind that this time is in a logarithmic scale. So basically what you would have is you would have a very steep going up of the curve and then kind of tailing. So as you can see, I show different temperatures here. So as temperature increases, your peak will get sharper and sharper. So how do we use this peak to actually determine my Henry's law constant? So that if you look at this equation here on the right-hand side, K actually indicates the dimensionless Henry's law constant, which I want to determine. And L is the length of the column that you're using in the gas chromatograph. And V indicates the linear velocity of the system. So of course you have to measure the volumetric flow rate divided by the area. The cross-sectional area of the column is going to give you your superficial velocity, and then using the epsilon, which is the porosity in the column, you can convert that to interstitial velocity. So I know all of these. I know L, I know V, and I know epsilon, which is the porosity of the column. So on the left-hand side here, mu indicates the first moment of this peak, which means that it is the mean residence time your samples using this mu, this integration under the curve. So integral from 0 to infinite, C dt actually indicates the area under one of these curves. So that's the integral at the bottom here, integral from 0 to infinite, C dt. And then by using, so mu d here actually indicates your dead time, which is the time that corresponds to the tubing and piping that's not really happening in the column. So you have to correct that time, your time, and then you do this integration again graphically, and that's going to give you your mu value, and equating that to the right-hand side, you can actually determine your K. So in this case, K is the isotherm slope. If you have a helium carrier gas, for example, and then you inject a carbon dioxide or nitrogen or any gas that is being adsorbed, it's going to give you your Henry's law constant because you have a pure helium carrier in the system. That means that the partial pressure of the component that is being adsorbed, your Henry's law constant. So what if I use mixed components in the carrier gas? For example, Take an example of a mixture of carbon dioxide and helium. We know that for all practical purposes, helium is not adsorbed at all or negligibly adsorbed under most circumstances. If I inject carbon dioxide into the pure helium carrier, I'm going to get my Henry's law constant. But what if I increase the carbon dioxide concentration in the gas? Let's say I'm just going to go up into here. So let's say I have this isotherm. I have a total pressure of 10 atmospheres, let's say, in the system, and then I adjust the mixture in the carrier gas so that I have a 50-50 mixture of carbon dioxide and helium. So what that really means is I have the partial pressure of carbon dioxide in the carrier gas as 5 atmosphere, right? So I am actually here at this point. So if I have and I'm assuming that helium is not adsorbed, and if it's not adsorbed, it's not going to affect the adsorption of CO2. It's not going to have any effect on the adsorption of CO2. So the Kp that I determined at this point, the K that I determined at this point, is going to give me the slope of the isotherm here. And I'm going to show you as an example in this following equation. So if I have this K, so this is the K that I get from this peak, which I can determine from the first moment. It's going to be related to the slope of the different isotherms in the mixture. So if I have a mixture of helium and carbon dioxide, and I know that helium is not adsorbed, and helium is going to be my second component. So what that really means is the slope of the isotherm for component 2, which in this case is helium, is going to be 0, because even Q is 0, the amount adsorbed for that component is 0. So of course its slope is going to be 0 as well. So if I have a mixture of 2 components where one of the components is not adsorbed, in the case helium, this is going to be actually negligible. So what I do here is then if I could determine my Kp value for different compositions of Y1, in this case, in the example that I use, let's say carbon dioxide, so I will be determining if I get Kp value at different Y1 values, and then if I integrate this equation, I will be able to get the pure component isotherm for component 1, in this case, carbon dioxide. So that's how I can actually determine the pure component isotherms by using this method, although it's not a very common method used for pure components because it's much easier much easier and more direct to determine the pure component isotherm gravimetrically or volumetrically. But I can apply this to the determination of the binary isotherms. And that's what I want to talk to you about today. But before going forward, I would like to come back to this slide here, where I'm actually determining this K, which is the dimensionless Henry's law constant here. So once I determine that, as I mentioned, if I have a binary mixture where one of the components is not adsorbed, that's going to give me the slope of the isotherm wherever that partial pressure is. So what I'm going to do is, this is dimensionless Henry's law constant, and convert it to the dimensional Henry's law constant, which is what I would need, by using this equation. By using the temperature and the density of the adsorbent pellet, I can convert the dimensionless K to the dimensional value, which I will need in this case, Kp. I have already talked about that, and I would like to come back to using this equation for determining the binary isotherm. So if I have a mixture in the carrier gas that both components are adsorbed, then in this case, I'm not going to be, this second term in this equation 1 is not going to be close to 0, and I have to consider that. So maybe this may be a good spot to take a pause and then get some questions, and if that's okay.
Yeah, we can. Thank you, Handan. We can do that. At the moment, there do not seem to be any questions in either the YouTube chat or Zoom. So attendees, please leave your questions. I guess I have an initial question, if we have time. So in the case where you have the binary mixture in the carrier gas, and then you then add some CO2 or nitrogen in the injection loop, and then that goes through the column.
Right.
What's the calibration procedure like for the TCD? Because now you have kind of a mixture on the reference side and now an unknown mixture on the sample side. Is that important to worry about?
Yes, that's what I'm going to talk about in the second half of my talk. But keep in mind that on the reference side, you have the mixture going in. So let's say we're looking at CO2 and nitrogen mixture, right? So on the reference side, your baseline is, before your carrier gas takes up the sample, your mixture is going through the system on both sample side as well as on the reference side. So you're going to have a zero baseline, right, before the injection.
Right.
So what happens is after the injection, the only difference that you have is relative to the mixture carrier. So once you pass your mixture, let's say carbon dioxide and nitrogen, which are both adsorbed in this case, and then you inject one component only, so let's say carbon dioxide, and then your TCD is going to pick up the difference between just the injected sample and then your mixture.
Right.
So relative to your baseline, it's going to see the difference between your mixture already and then a small injection.
Right, thank you. So you assume that there's like a linear relationship between the concentration and the thermal conductivity.
You don't even have to, because okay, in a typical gas chromatograph, you actually have your sample side and then your reference side are going in parallel. But in this case, keep in mind that I'm doing it in series. So on the reference side, so maybe if I could go back to the schematic diagram here. So I already have the mixture going through the reference side of the TCD. And then it's going through the reference side, taking up the sample, going to, again, one at a time. I'm not injecting a mixture. I'm injecting either CO2 or nitrogen into the system. So the only thing that the TCD sees, the response sees, is the difference of, let's say, if I'm injecting CO2, just the CO2 as opposed to the CO2 and nitrogen mixture. Does that make sense?
Right, yes, thank you. Yeah. We have a question that's come through, and I think after that we can probably resume the talk. It's from Nicholas Wilkins, and he says, thank you, Dr. Tezel. Can this be applied outside of the linear isotherm region?
Oh, I couldn't hear you. Can this be applied?
Sorry, the question was, thank you, Dr. Tezel. Can this be applied outside of the linear isotherm region?
Absolutely, absolutely. Because what this KP indicates is if it's a pure component isotherm, it is the slope of the isotherm at that partial pressure. So as I mentioned, in the case of carbon dioxide and helium, for example, where helium is not adsorbed, it will be the slope. So if I go back here, so let's say, as I mentioned, if I have a total pressure of 10 atmosphere, and if I have a 50-50 mixture of CO2 and helium, that means that my partial pressure of CO2 is 5 atmosphere, and I'm not in the linear region here. What I get as Kp is the slope of the isotherm at this point. So what I do is I do this, let's say, keeping the total pressure 10 atmospheres, and then I keep changing the CO2 concentration in the gas. Let's say if I'm at 10% CO2, that means that the partial pressure of CO2 is 1 atmosphere, and then I get the slope here. So at different compositions, I will get the slope, whatever I have. Yes, so basically that will be applied to a nonlinear isotherm as well.
Thank you very much. With that, if you don't mind, we can probably resume the rest of your talk.
Of course. Okay, so so we have talked about how we can determine the pure component isotherms by using a mixture of adsorbed component and a non-adsorbed component. Usually helium is used as a non-adsorbing gas. And then in the case of, if I want to apply this to binary mixtures, of course, in this equation 1, the second term on the right-hand side is not going to be negligible. And these are the slope of the isotherms in the binary case. So the Kp that I will determine will be a combination of the slope of the individual binary isotherms multiplied by concentration. So in this case, for example, here, since I have a binary system, y1 plus y2 is equal to 1. And these y values are the mole fraction of the individual components. So in this case, we usually indicate as component 1 the more adsorbed component. So for example, in the case of CO2 and nitrogen, CO2 is generally more adsorbed. So my component 1 will be CO2. So 1 minus y1 is going to give me the mole fraction of the nitrogen, multiplied by the slope of the CO2 isotherm plus the mole fraction of component 1, which is CO2 in this case, multiplied by the slope of the adsorption isotherm of nitrogen. So how do we deal with that? So the way we do this is, again, we determine the Kp value, which I have indicated experimentally how we determine that for different compositions, at different compositions. And then we do this plot on the left-hand side. So we have Kp as a function of the mole fraction of the gas that is being adsorbed. So in this case that I've given here is the BPL activated carbon for methane and CO2. And in this case, methane is adsorbed more, and then we get the Kp value as a function of the mole fraction of the gas phase, which is the carrier gas, and then we determine the Kp values. So this is a beautiful linear line that we get, but unfortunately, as most of you know, we don't get these beautiful linear lines all the time for all systems. So if we go to the next slide, as you can see here on the left-hand side, this is a Kp determined experimentally as a function of the mole fraction of the gases in this case. This is an example of a carbon dioxide and nitrogen on silicalite. So we get this, you see these data points here, it starts very high and then suddenly goes down and then, tails down here. Excuse me. So because this is a very sudden change compared to the linear line, so I have actually blown up this section of the figure to see the differences in different models. So how do we handle that? So the most important thing is to express this behavior of Kp as a function of mole fraction with a proper model. So this methodology actually started in 1970s, as you will see from the references. These are just sample references and by no means indicate all the work that has been done here, but I just show some examples of references. So the first thing that people did is basically, how about we use a linear equation? So as you can see here on the right-hand side, I have actually summarized some of the equations that have been used to express this behavior. So starting with the easy linear, easy polymeric behavior. So as you can see here, it's the third degree polynomial, and then it has 4 parameters. So what you do is you do a curve fit to this equation, and then that is the most important with this method. That's the most important thing that you have to do. You find a model that express your Kp as a function of mole fraction in the gas phase, and then the rest is easy. Once you have a good model that shows your behavior. So what you do here, different models have been used, but I'm going to use an example of the polynomial because that's kind of more easy to explain. So once you have a model here, let's say polynomial, third degree polynomial, you take the derivative of this function and then you express your isotherm slopes through that equation, but of course using different parameters. So in this case, let's say if I have a good fit for a polynomial equation, let's say third degree polynomial, when you take the derivative of that equation, you will end up with a second degree polynomial, and then you express your slope of your isotherms with that equation. So in this case, second degree polynomial, and then B and C coefficients you need to determine. And then what you do is once you express them in a certain way, by integrating those equations, you get the binary isotherm. So in the polynomial case, for example, these are the equations given for Q1 and Q2. So, and then if you have another function, so we've tried other functions combining the polynomial with inverse functions here. And then we've also tried combining the polynomial with a logarithmic function. Again, the same thing. You express your slope of the isotherms with a derivative equation with different parameters, B and C coefficients, and then once you integrate those, you get your binary isotherm. So these are the 3 models that we tried with my latest student, Dean Kennedy, who just finished his PhD this year. So we tried these models, and we've seen that they were not really a good fit for this system. Silicalite with CO2 and nitrogen. So as you can see here, this dashed line indicates the polynomial. It's not doing very well. And then we have this dash dot is MTT, didn't work well. And then HT, CPM seemed to work a bit better than the others, but still not good. So we had to come up with a different model to actually express, and here is what we did. So if we look at, so we combine a logarithmic function with an exponential, and as you can see here, that was the best one that actually expressed our behavior. And then what you do, so keep this logarithmic and exponential term, and then you come in here, you express your slope of your isotherms by the derivative of this. So as you can see, For example, if you look at equation 3, if I take the integral of the first term, I would get an ln term. And if I integrate the second term, the exponential function, I will get an exponential term, which will actually give me the equation for my Kp versus composition curve fit. So once I express these binary isotherms in terms of coefficients B1, B2, C1, C2, and then I have other two coefficients, alpha and lambda here. All I need to do is determine these coefficients, and I'm going to talk about that, how we do that. And then once I determine these coefficients, I integrate these terms, and knowing all my coefficients, I get the binary isotherms. So how do I determine the coefficients, these coefficients in the derivatives? So if you remember equation 1, remember the Kp was a function of the mole fraction of the second component times the derivative of the first component plus mole fraction of the first component times the derivative of the second component. So this was equation 1, and I put these coefficients, these derivatives with the coefficients into equation 1 to get this equation. So what I really need to do is determine these coefficients, and I do that comparing these Kp values that I get experimentally at different compositions of the carrier gas, and I do a sum of square residuals. So basically this is my experimental Kp value, and then the second term here is the equation that I came up with, which should be equal to my Kp, and then I take the difference, I square them, and I add them for different values of y1 from 0 to 1, and I determine the sum of square residuals, and I minimize the sum of square residuals, and that's how I can actually determine these coefficients. So keep in mind that I have 6 coefficients here, so I have to have at least, I have to have much more data points than 6, right? So that just having 6 data points is not going to be enough, because I have to do minimize the sum of square residuals. So I have the more data points I get, the better my determination will be. So of course, when you do this determination of the coefficients, you may end up with multiple solutions. And how do we avoid that? By using some constraints, because these coefficients that you will get will have to make some physical sense. So what we do, for example, in this case, I have listed 3 constraints here. The isotherm slopes should always be greater than 0, because you're not going to have a maximum in your isotherm. So the isotherm slope should always be positive. And then at the 2 extremes, where you have mole fractions of component 1 at 0 and at 1, your Kp values should exactly fit your Kp. So by using these constraints, you determine these B and C coefficients, and then what you do is, after you determine these coefficients, you put them into these equations. This is an example equation that we use for the CO2 and nitrogen on silicalite, and then you get your Q1 and Q2 values. So that's how actually we can determine the binary isotherms. So how does that work? How does this method compare with other methods that the people have used in the past? So so this is another example of, sorry, I forgot to mention the slide before going to the comparison, but here are the sum of square residuals that are listed here, with the linear line, the polynomial one is MVV, which is the blue one here. As you can see, it's not doing really well. Again, this is we're still with silica halide with CO2 and nitrogen. As you can see, the sum of square residuals is minimum for the combination of the logarithmic and the exponential function. And then here we have the binary isotherms we have done for this system. Again, silica halide with CO2 and nitrogen. And then you can do this at different total pressures. Here are some examples for CO2 and nitrogen. As you will see, the black lines are the ones at 1 atmosphere, and then the green ones given at 2 atmospheres, 3, 4, and 5 total pressures. As you can see, as you increase your total pressure, your amount absorbed is going to increase for both of your components, both nitrogen and CO2 here is actually increasing as you increase the total pressure. So how does this compare with other methods? So in 2003, with my PhD student at the time, Peter Harlick, we looked at this. And so we have looked at some more linear looking isotherms as well as more nonlinear looking isotherms. And then we have seen that the fits were, the comparisons were quite good. So in this example, we have the experimental data from Hoon and Denner from 1982. So you can see the data points here for CO2 and C2H4 and the data points here, and then the models that we have, TT and HT-CPM. They're right on top of each other. You cannot see the difference, but you can see the polynomial one, the dash line, that one does not work very well, but the other ones actually work quite well. So then the other system that we compared it was the C2H6 and C2H4. As you can see, these are the data points are given as circles. And then the HT-CPM, the solid lines actually work much better in this case than the other functions. So as I mentioned here, the best thing to do here is to determine a good equation, to find a good model to represent your Kp as a function of composition, and then you're all set. So conclusions, the accuracy of the Kp regression is greatly affected by how good a model you find for your Kp as a function of your composition in the carrier gas. Once you have a good model for that, as I mentioned, you take the derivative function of that and then put in your B and C coefficients and do the minimize the sum of square residuals, determine your B and C coefficients, and then by integrating your slope of the isotherms, you determine your binary isotherms. So as you can see, this method agrees pretty well with the binary isotherms determined by using other methods. It's much better than you cannot really use the ideal adsorbed solution theory or other methods because you have to experimentally prove that this is the actual behavior, and it's very hard for most systems to do that by using ideal adsorbed solution theory or vacancy solution theory, whatever you might have. They're all predictions. You have to really determine that experimentally. So with that, I would like to thank International to talk to you about this method, and then for the funding that I have received, the discovery grant funding I received from NSERC, and my former supervisor, Doug Ruben, who actually got me into this beautiful adsorption field, and I'm having lots of fun with it since then. And of course, the students who are actually doing the work. So those are the names of my students who actually worked on this. And I would like to thank you for your attention. This is a picture of my group taking at the good old times when we didn't have to wear masks, where we didn't have to social distance. And so anyway, and thank you for your attention. If you have any further questions, I'll be able to answer them now, or here is my contact information. You can get in touch with me anytime. And thank you, that's all.
Thank you very much again, Handan. We do have a question from Zoom. It's from Professor Andreas Ziedel-Morgenstern. And he would like to know, or if you have any comments on how to extend this method to 3 components or more than 2 components.
Yeah, I don't think you can do that with this method because I haven't looked into that. That's very interesting. Can it be extrapolated to more than 2 components? Possibly. Then you have to find, instead of finding a 2-dimensional equation, then you have to find, let's say if you have a 3-component, then you have to find a function that's going to give you a surface. So instead of fitting an equation, then you have to fit a surface. For the 3-component, that could be done, but that will require some fancy curve fitting techniques.
Right, thank you. We have another question from Daniel Siderius. He says, thank you for the talk. And how do you estimate the volume of the injected sample?
Yeah, that's a good point. So the volume of the injected sample has to be as low as possible. What we use is about 1 cc. So in the gas chromatograph, we have a 1 milliliter loop that we inject. So you really need to optimize that size of because if your sample size is very small, let's say if you inject a microliter, that's not going to give you a very big peak that you can get the integral under the curve accurately. So you have to, it has to be minimum, but you have to optimize it with your peak size. So you have to optimize your sample size. We generally use about 1 cc sample loop, and that seems to work well. Now, another thing that I would like to mention is that you can inject CO2 and you can inject nitrogen, let's say, if you're looking at a mixture of CO2 and nitrogen. And we have seen that one of the components injections, it always increases slightly. And then for the other component, it consistently decreases the Kp value slightly. But that makes sense because what you're doing is by injecting one of the components, you're slightly increasing the partial pressure of that component in the mixture. So you're kind of moving your slope, moving your composition slightly to the right or to the left as far as composition is concerned, depending on which component you are in. So, yeah.
Thank you very much. I have a kind of a related question to that, or about the experimental setup. Do you observe any heat effects of the column? So the column's in the kind of air bath of the GC. And I guess for very strongly adsorbing species, does that have any effect on the peak shape?
Now, keep in mind that before you, as far as the heat effects is concerned, you can definitely do that at any temperature that you want, as long as you control the gas chromatographic oven at a certain temperature. And then you have to obviously, I haven't mentioned that, but you have to actually make sure that your baseline is linear. So which means that your mixture carrier is in full thermodynamic equilibrium at that composition. And you will have these heat effects until you come to thermodynamic equilibrium with the whatever the composition that you're dealing with. But then after it's at equilibrium, let's say when your carrier gas is going through the system, through the reference side, before you inject your sample, everything should be at thermodynamic equilibrium, both concentration-wise as well as the temperature-wise. So then by injecting one of the components should not really have heat effects. Because you're injecting a very small sample. I'm assuming that, like in all of our calculations, we have all assumed that it's isothermal, and then the temperature stays constant. And so because you're injecting a very small sample, it's very reasonable to assume that it's at thermal equilibrium as well.
Right, thank you very much for your answer. We have a comment from Andreas, and I think that might be the last one for today, given the time. In response to his first question, he says, you might then need to extend the local slopes of the partial isotherms at the saturation concentration with the multi-component situation.
Okay, so it's an interesting question, but does he mean saturation or equilibrium? I guess usually when we say
I think it is the plateau concentration. So when you have multiple components, when you have the intermediate plateaus that are formed because of the competition.
So of course, yeah, when you have multiple, I mean, at plateau, you would have, the slope will be 0, right? For that component. Yes, so I'm assuming that, Andreas, you mean what if one of the component actually gets to saturation before the other component, then it will not have any effect, right? So when you deal with 3-component systems, that will be an issue. But for a binary system, we usually have the pure component isotherm data before we decide to do the binary component isotherm. So we will have a more or less an idea as to where the saturation happens for each of the components. And then if you're, let's say, if you're at a situation where you're above the saturation of one of the components, that means that your slope of that component is going to be 0 in equation 1, and then you're basically dealing with the other component only. Interesting question. Thank you.
Yeah, he says he will follow up with you by email. There's also another question in Zoom, but I think I'll also request that Bassam follows up with you by email as well. So again, thank you for your nice talk and introducing us to this method. I think Arvind has a few words to say to wrap up as well.
Thank you very much, and very interesting questions. Please follow up with me with email.
David, you want to say a few words about the Twitter?
Sure. Thanks again for everyone for attending this session. The International Adsorption Society is running its inaugural online Twitter poster conference next week. So it's running from the 7th to the 11th of December. It's a no-cost event. Please attend this link for more information and to register. You don't have to attend every day of the session. You can attend as much or as little as you like. The good news is we have secured some generous sponsors. So we have 5 Best Poster Awards available to award as well for the session. So please check that out. Please forward it on to your colleagues and co-workers, and we hope to see you there.
Just to wrap up, and then just to point out, the Twitter poster contest is entirely run by students. So I would encourage all graduate students and undergraduate students to consider participation. So we are thankful that you were able to attend today's webinar. So the next webinar for January will be announced either on Twitter and it's not either, on Twitter and on the IAS mailing list. So please do follow that. And on behalf of the International Adsorption Society and its members, I wish you all a good holiday season. Thank you and bye-bye.